let me introduce you our guest. It is Francesco from GreenWaves Technologies. He will be giving a talk about edge computing and very interesting processes, that they're developing in their company. And please give a talk.
Thank you. Thank you for the introduction, and thanks for inviting us to Ilya and all experienced team. Okay, so we probably all know. I think that probably most of you they are coming from AI, machine learning, and also I don't know, maybe someone from embedded systems also. That AI is moving to the edge, so to small devices, because of a number of reasons. Which can be related to IoT field, but also on other surveillance devices. Also, the market related to automotive, mobile, and so we have different problems that we have to tackle if we have to deploy something in the cloud. So and mostly is related to four different problems. One is that then the data needs to go back and forth, and then we have to build more and more bigger cloud. We have a privacy issue when we then transfer data. We would like to have a decision latency, which is a smaller decision latency, and also we have power concerns because transmitting data over Wi-Fi, it's asking for power. So this is what we do and what we try to tackle. So to bring machine learning and artificial intelligence to the edge, and these are the problems that we try to solve. So in a sense that we try to solve that with some compute state. So we try to have, we need to have something which is scalable to the consumption workload, so that we can, for example, have a chip that is on when we need it, but then when there are parts of the chip that we don't need, we can turn it off, or for example, we can put in sleep state or turn off the system. We need to have under control the absolute consumption rate if you want to have something which is battery powered, and also the speed between the transition state should be fast. We cannot like wait for 1 minute to boot up something. And also we need to support a wide range of compute tasks, which actually can range from acquisition, so drivers, pre-processing, but also standard algorithm related to all inference in NN, but other algorithmics. So another point is to have something which can support a wide range of application, and which algorithms are changing, because we've seen that in a few years we see a lot of changing. For example, if we talk about neural networks, we see that layers changes, architecture changes. So let me spend a little bit of time in presenting who we are. So GreenWaves Technologies is a company which has been founded in 2014 in Grenoble, France. We have been developing our first product, our first chip, which is called GAP8 in May 2016. And then we launched the GAP8 in February 2018. We shipped some dev kits, and we also opened a couple of offices, one in Bologna, Italy, and the second one in Shanghai. And we launched a second product, which is called GAP9. And now we are around 51 employees in these three offices. I will present here three main concepts, which are the one that we use to design our chips. The first one is to have high compute at low power. So is trying to have exploit different architectures to being able to have high MIPS per watt. The second one is to be agile, so to have the ability to change state quickly, and also to turn on and off part of the chip or the complete chip when it's not needed, and to have sleep state which consumes few microamps. And the second one is to be flexible, so to be fully programmable. We see that there are a lot of chip vendors that have done accelerators. We see a lot of neural accelerators, but then usually you want to add some pre-filtering or some post-processing, pre-processing. You would like to add other blocks. Usually it's not only even if it's a neural network, it's not only neural network. So that's why we try to keep it flexible, because algorithms are changing. So betting on one architecture then can lead to have something which is not usable, because then from the starting day where you start designing your chip and then the day you have it out, it takes few years. We have open source origins in a sense that the chip that we have are coming from the instruction set architecture is coming from RISC-V, which is an open source instruction set, and also we've been involved in a project which is called PAL, which stands for Parallel Ultra Low Power Platform, and which is developed in ETH Zurich and University of Bologna, and which we have been contributors, and we are still contributors with them. And then it's where it's coming GAP8, and which is leveraging some of the work that Pulp is doing. I'll spend one slide explaining a little bit the architecture of the chip, to give you an idea of what does it mean to have different states and different part of the chip that can be turned on and off, and also what the chip features. So we have a first part of the chip which we call fabric controller, which is mostly like an MCU. So it's we have one core which is a RISC-V core. We have 512 kilobytes of memory, of main L2 memory, and then we have lots of peripherals to communicate with all the possible input and output that we have. So, for example, we have CPI that we use for cameras. We have Quad SPI and Hyperbus to connect external memories. So usually if we gonna have a flash memory outside the chip, which could be 64 and even I think 128 up to 128 megabytes, and also an external RAM, because often we need to store some data which is then accessed from the chip in a larger memory than 512 kilobytes. Even, I mean, if we start playing with VGA images in 3 color, then 512 kilobytes, it's quite small. And to communicate with the peripheral, we have what we call a micro DMA, which is a DMA that can, it's a little bit more smart than a DMA, so it can also do 2D copies and transfer the data, so you can offload the handling of the peripherals to this block. And then we have a second part of the chip, which we call cluster, and which is a cluster of 8 cores, which are 8 RISC-V cores. And so they are fully programmable cores, and which share an instruction cache and share a 64 kilobytes of L1 memory, which can be accessed in one cycle. To communicate between memory, I mean, each of the cores can access directly all the memories that are inside the chip, but also we can use cluster DMA to hide memory movement while the core are working on their tasks. Okay. So how do we program this thing? So we have some RTOS, which we provide with our SDK. We have two main supported OS. One is FreeRTOS, and another one is called PulpOS, and is coming from the Pulp project. We have a system on chip simulator, which we call GVSOC, and which can actually be downloaded from in our SDK and can be used to develop without having the chip in hand. It's also quite handy to debug code, and it's quite accurate also in when you want to measure cycles. We try to keep the error between the performance that you get on the chip and on the simulator under 10%. It's usually well under 10%, but you can get up to that. So it's good also to have an idea of how many cycles will take the code that you developed. And we have a RISC-V GCC toolchain. Then we have high-level tool, and I will concentrate my presentation on this part here, which are tools related to handle NN coming from frameworks, but also to ease the programming of the chip. So we have three different mode where the chip can operate. So we have sleep mode with retention in the L2 memory, where we consume few microwatt. Then we can turn on only the fabric controller, and the fabric controller can is turned on at 50 megahertz, but can go up to 250 megahertz, and it's consuming around few milliwatt. And then we can turn on the full chip, so then the fabric controller can switch on the cluster, and then we have power consumption, which is below 100 milliwatt. Okay, so there are four things which made us unique in terms of the performance that we can deliver per watt. And I will explain here these 4 points. The first one is that we added to the instruction set some DSP extensions, some SIM instruction and some bit manipulation. And also we have vector units where we can do 4 operation on bytes or 2 operation on AL4 per cycles. We have an efficient parallelization. So when the core 0 dispatch to the other cores a function to be executed, it takes only a few cycles. And even if the cluster, for example, is on, but there is nothing, there is no task executing on the cluster, the core are clock gated, and we implemented this technique to consume less power. Then all the cores in the cluster share an instruction cache, which is reducing actually the fetching, the instruction fetching, in case you want to fetch the same instruction for the same cores. And also we don't implement caches. So even if they are called L1, L2, L3, these are just levels, but they are not caches but they are these are memories that are explicitly addressed. So which enables us, if we know that we gonna implement algorithms which have predictable data movement to program the DMA, and so to avoid all the circuitry that is needed in caches to keep them fresh and to load data. And also we avoid all the cache misses that we're gonna have. And the fourth one is that we have fast hardware state changes. So to give you an idea of how we compare with an STM32H7, here we took CFR10 and MobileNet V1 reduced that are running at the same frame rate on GAP8 and on the STM32. And so we implement the same network with the same accuracy. GAP8, it's done in 55 nanometer, so it's an older technology than the STM32, and we can see that the milliwatt for CFR10 they are 60 with relation to GAP, which is 3.7, so it's a 16 per less power. And I mean here a milliwatt, and that can be automatically converted into millijoules since the execution is the same. So we implemented in GAP in a way that the execution time for the task is the same. And for MobileNet V1, this is a version which is reduced because the STM32 doesn't have enough memory to run it. Okay, so here is an overview of the architecture, but I like to say that this is only 50% of the story, because yeah, okay, you can implement a lot of tricks and a lot of architectural choices to have a good architecture, but then you also have to provide tools that is the work of the developers. So there are a few challenges. Then if you look at this architecture and you want to then port your application to GAP, there are a few challenges that you need to tackle. The first one is that you have parallel cores, so you have to know how to parallel program. The second one is that there are vector units. So we provide built-ins. So it's not code which is written in assembly, but still we provide built-ins. So you have to know these instructions and to use them and to place properly data in memory to exploit the built-ins. And also, we've just seen that we have these hierarchical memories. And so the data movement should be done by hand. So when you start your application, the data is in flash. Actually the code is loaded, and then the data also, and then is produced. And then when you put data in L2 or in L3 inside L1, and then also since we can use DMA to move data, we have also to think about the fact that we can tile the code and tile the data, and then so hide movement that are done between the DMA while the cores are executing their job on a previous loaded part of the data. Then there are other 2 points. The first one is related to integer arithmetic. So we don't have floating point unit, so we need actually to quantize our neural networks or also our algorithms. You can still do a few operations in floating point, but these are emulated, so they are not really efficient. And the last point, it's usually we do exploit machine learning frameworks, so to train our algorithms. So we would like to automate the graph and all the nodes dependency extraction, and also the model, so how to extract the model and then put into GAP. So to tackle this, tackle all the problem that that we have to build an application based on machine learning, we have a few steps. So we have to collect data, we have to train our models, and then usually if we want to go to tiny platform, we have to go to a graph conversion step, and then here then we place GAPflow, so which is actually taking this graph and bringing them to GAP. This GAPflow, it's made of these two main blocks. One is called GAP NNtool, which is producing what we call an autotiler model, and then we have an autotiler which is producing then C code that can be run on the chip, and also in the GV socket in the virtual platform. So this GAP NNtool, it's able to import a TensorFlow Lite or an ONNX graph, then can actually map and look at all the layers and all the computational nodes, and also have an internal representation of them as tools for quantization and calibration on the dataset, and produce this autotiler model. This autotiler model, this autotiler is a tool which optimizes the memory movement and automatically generates the memory movement, in the sense that given a constraint of sizes in L1, L2, L3 memories, this is and also the data path that the algorithm it's requiring to execute all the layer, if we are talking about a neural network, then it's actually computing the optimal memory movement. Okay, so about this this memory movement, there are a few constraints that we need to tackle. So it's where we store data. So ideally, we would like to turn on the system, and then if we need to offload a task when we want to execute our neural network on the cluster, ideally we would like to store all the data in L1. So copy the data to run our job, but then in 64 kilobytes, they are quite small. So we need to deal with where we can store the static parameters and the activation, so the dynamic parameters, which are the I/O of our layers. We need to tile the data, so to work on tiling to actually reduce the overhead and hide the overhead, so that while we transfer data in L1, part of the data can be already processed by the cores. And also then we have to implement this double buffer mechanism. So where, for example, if we have an image, we can divide in multiple tiles. And if you want to apply a convolution, we can copy the first two tiles, make the cores working on first two tiles, and then ask in the meantime to the DMA to move the data. And this is actually tackling with this explicit memory handling, which I was talking before. And so for this, we made this GAP autotiler, which is made of four main blocks. The first one is basic kernels, which is a library of individual computing kernels, which can map 8 or 16-bit input-output to the cluster. Generators, which are made to generate this tiled code and all the memory movement. Then we have an IT model, which is calls this generator, which actually generate the memory movement. And for example, the IT model is made of all the node graph, the node that you have in your graph in your neural network. And we have a graph description, so which is actually describing all the dependencies between the nodes. So why do we need this complicated three things? So the first, the basic kernels, It's because we would like to have to write convolution, for example, here convolution 3 by 3. We would like to write it once, and one we've written, the convolution is done, and it's optimized. It's using the vector units, and in this way we can write it once and write in a way that is thinking that all the data that is needed it's in L1. So so we have done it, we have written it, and we can use it for all the other 3 by 3 convolution that we have. And we provide a lot of basic kernels, but and they are open source, so you can actually go and add your own basic kernel if you want to do something which is not already optimized. And this is how we actually solve the problem of parallel programming and built-ins. So, which from one side we provide all these kernels, which but from the other side they are open source, so you can take a look into it, change it, and even improve them. So then why we need to do model and graph layer optimization? So why do we have this auto-tiler model and this graph level description? Because here, if we take, for example, a simple network, I think this is MNIST. We have a TF-like graph, which is extracted from Netron. So we see that comp2D activation and max pooling, they are 3 different layers. This actually, if we implement in this way in our system, it actually means that if we load all the network data in L2, then to do the convolution, we need to move the input image to L1, then do the convolution on the cores, then bring the results back and do it again for the reload and for the max pooling, which is not very optimal, because convolution then followed by a reload and max pool can actually exploit the locality of data. So in this way we can reduce a lot the memory movement that we have, and once we have the result of our convolution locally, we can then make follow reload and max pooling. So on the right here, we have how we represent and why we need to have this conversion is because, for example, for this example, you can have a generator which is generating a layer which is convolution plus reload plus max pooling, so that the data is fetched once for each of the tiles of the data. And then, so instead of having repeating for this example in NIST 2 times these 3 steps, we have just 2 layers which are doing group convolution, reload, and max pooling. So and also another point for which we made this automatic generation of memory movement is that if we take another network which is composed of 3 layers, which are convolutional layers, we have only weights, we don't have biases. For simplicity, we have an input and an output, and we have some activations. So what happens before the execution of our code, we flash the code and the weights in the flash. Then when we start executing, we need to find which is where is the best place to move and to place the weights before the network execution. And ideally, if they are big enough, we will put them in L1. But if they don't fit L1, some of them we can put in L2 or in L3, and then we need also to keep into account the fact that we need to save some output of the activations and also the final output. So that's why we have an AT model, and taking this AT auto-tiler model and graph description, the autotiler optimizes where to put this data given the constraint of the memory. So you can give a 64 kilobyte of memory in L1, given into account, also to keep into account that in this 64 kilobyte, there should be also the stacks for the cores. So it should be a little bit smaller, at least, I don't know, it depends how many stack, but how much stack you will give, but 6 kilobytes or even more for the stack. And also, we need to take into account also that maybe all the L2 memory, you would like to do something else, not only all the execution of your neural network. So instead of using 512 kilobyte of memory, you would like to use less. And then if tomorrow you want to change the network, so you want to change the input size, this thing needs to be redone again. So that's what the autotiler does. So it takes all these constraints and optimize the memory movement, which means that if tomorrow you change the size of the input and then so the first layer, all the memory movement can be automatically generated again. And this is how we deal with this explicit memory handling. From a working point of view, so this is the working scheme of the autotiler. So we have these models, which is expressing the nodes that we have in our network plus the graph. And then we call generators, which are actually so for the layers, the grouped layers that we have in our network. And this is executed on the host using the autotiler engine. So the optimizer, we produce an x86 binary, which then is executed on the PC and produce what we call user kernels, which are all the layers of your network plus all the memory movements. And then if you want to write your own application, you need to write your user code that then calls this kernel and that exploit the basic kernel, so the units that are actually doing the job. Okay, so how these things look like? So you actually have two files generated, which contain these user kernels. And you have a binary data file, which is containing all the weights, biases, and all the information needed by the network to execute. And from the end user perspective, you have then generated three calls. One is to construct the network, which is actually to place at the beginning of ahead of the execution in the right place all the data, and also to allocate the memory that it's going to be needed for the network to execute. Then you have another call, which is executing the network, and one to deallocate the memory. So if I can give an example, let's say that here we want to open a camera. So we have a simple application, which is opening camera, collecting images, and running mobile net on it. So we have some calls at the beginning, which are allocating L2 memory for the input. We need to turn on the camera, then we need to turn on the cluster, and we create a task which is dispatched to the cluster with as argument the input image and the execution, which is the function which is executing, which is executed on the cluster. Then we call the construction, and then we do a loop, which is collecting an image and then crawling the cluster, so dispatching this image on the cluster. And then once we finish, in this case, never, but because it's while one, but if there are other conditions met, you can construct deallocate and do something else or stop the execution. Okay, so with this autotiler, we actually cope with these three challenges. So the challenges, so the vector units, the how to program parallel code, and also how to handle explicitly the memories. The other 2 points which are still there is how to cope with integer arithmetics. and also how to import data from the graph that we have been training with our Keras or our PyTorch. And also, if we look at the slide before, we have added another problem, which is how do we generate this autotiler model and this graph. So for this, we have developed this tool, which is called NNtool, which is importing TensorFlow Lite and ONNX graph and generates an autotiler model. And also it's able to control some features. So you can explicitly say how many memory you would like your algorithm to run on. But also has other features like post-training quantization or loading of the statistics from a quantized TF Lite, and some tools, some commands for debugging. So how you can debug basic kernels, and also how you can validate the model against the inference that you have on a PC. So this is some of the functional blocks. So we load a model that is then described inside the tool, and then there is code generation blocks which generate this autotiler model. But also you can import your dataset and apply quantization, 16-bit or 8-bit quantization. And then you can also check, since we have the GAP-like functional kernels, so we have kernels which execute in fixed point. You can also check the accuracy that you get with the quantized version of your network, or validate the results that you have against floating point, against fixed point, but you can also use it for model debug. So to give you an idea, this is a Python tool, you can just call it. You can just source our SDK and call through NNtool, and then you have a lot of commands that you can execute. If we want to port a quantized network, we can load it with a specific command, and with -q we can import the quantization, which is the statistic which are already present in the TF Lite if they are, and we can show with the command show all the layers and all the information related to the network, how they were loaded. Then we need to apply two adjustments. The first one is related to the first one. It's more related to the data layout. So, for example, TensorFlow Lite is channel last, while our kernels are channel first. So we need to adjust all the network. And also, we need to apply another command, which is called fusions, which is actually looking for kernels that can be fused together. Because obviously, I didn't mention, but we also have a layer for convolution in the autotiler. We also have a pooling layer and the ReLU layer separately. But if we can put them together, then they will be more optimized, so consume less and run faster. Then we can also show the quantization scheme and the information about it. And then we can generate this autotiler model that then can be executed and generate the user kernels. On the quantization, we have a specific command, and we support two quantization scheme. One, which is a TensorFlow Lite quantization, which is asymmetric and is the default one. And the second one, which is more an historical one, so it's the first one that we implemented, and it's a symmetric quantization, which we call power of 2. And then when you do quantization, you need to load the dataset, a dataset or part of the dataset that is then used to apply post-training quantization. Then to debug the model, you have a specific command which is called DAM, which is executing the network on an image. The -q is saying that you want to execute the quantized version, and the -t because you want to print out the quantized, so that, for example, you can see floating point number and check your quantized version, which is printed out in floating point numbers, against the floating point version. And then we have a special command called tensor, and another one which is called Q error, which is showing which is the quantization error that you get on a specific image. So it's showing the QSNR of all the layers. Or you can then look at single layers to see, for example, if there is one layer which is not quantized correctly or is giving problem in quantization. Okay, so to make a summary, so GAPflow is trying to automate this end-to-end process to port neural network from and high-level machine learning frameworks onto GAP. And is composed of this autotiler, which integrates highly optimized kernels, which can be deployed on GAP, and is generating all the memory movement so that given memory constraint. And NNtool is a Python tool that we can use to load our network and produce this autotiler model. So we have what we call an N menu, which is a collection of examples that show how these tools works. It is organized in 3 different folders. So one is that we call ingredients, where you can go and actually there are some examples which are well-known networks. Like, for example, there is a repository with most of the MobileNet family networks, and and you can run them, see the performance that you get, and see how from the TensorFlow Lite or also the PyTorch you go onto GAP using all these tools. We have a second folder which is implementing some use case specific networks, and also has drivers so that you can use the camera, or if you have a screen, so it's more complete examples. And then you have what we call main courses, which are application which has a specific board to run on. And here we have 2 of them. One is related to occupancy management, and it's a board which is counting people with an infrared sensor. And the second one has been developed, and the second one that we have, it's a face re-identification. So I give you just a couple of examples of what we have. This is related to the MobileNet image family. And so if we look at these are all you can see in the two in the 2 charts. You see the energy consumption of all the family related to MobileNet V1 and V2. So here in this example, it's missing the V3, and you can see that at GAP8 at the max power consumption, frequency on the cluster and on the FC, it's consuming up to 112 milliwatt. This is including also external memory, and it's going from the smaller MobileNet that is consuming 1.5 millijoule to the bigger one, which is consuming 55, and it's running at around 2 frames per second. And another example, it's that is I think it's interesting. It's this example called showing how we can do a license plate recognition, and is composed of 2 different networks. One, it's an SSD object detection network, which is detecting the license plate, and then there is a network called LPRnet, which is kind of OCR. And this is interesting because it's showing how we couple multiple networks, and this is a quite big network for GAP8. because we have more than 4 MB of memory footprint, and but we have a quite good accuracy on the two networks, on the SSD part and on the LPRnet also, and an inference costs around 108 millijoule. What is interesting is that we've been publishing a paper on this, and if we look at other results related to which are running on bigger system like Raspberry or other boards, we are a lot more and more energy efficient with relation to all the others. And that's it. Thank you. I don't know if there are questions. I hope I've not been too long.
Yeah, thanks for your presentation. Can I ask you about coverage of operations that your tool supports? I mean, do you support all operations from the full light or not?
No, we don't support all the operations. Anas, please go ahead.
Yeah, and what's the percentage, or probably how you solve this problem? You are trying to change your network to
so there are
on your devices. Yeah, you have to change the architecture. Yeah.
So I think there are two main points here. One is related to the layers that you support in a network. So and here we mostly support convolutional layers, so depth-wise, also dilation, and so most of the convolutional layers, I think we support with all the different variants. We've been adding also support to RNN, so we support LSTM and GRUs. Then we have lots of starting to add lots of math operators, and it's here that the thing became tricky, and also to all the parts related to sometimes there are some kind of strange operators. So we started actually NNtool at the beginning was supporting only TensorFlow Lite, and this is because TensorFlow Lite is giving a simpler, is simplifying actually the network with relation to TensorFlow itself, so to having a PB file. And then while we were adding all support also to math operators, we also added the ONNX. I mean, at the beginning, we started designing with the idea that you can actually change your, in most of the cases, actually, you can change a little bit the architecture of your network to match the tools. But then we understood that this is not actually working in terms of user experience and also in terms of productivity. So we started adding tools, and we try to listen to GitHub and all our clients when they have problem and they want to support a network, and we add it or a specific operator. On the other side, all these tools except the generator of the autotiler, but NNtool and when I talk about the generator, is the engine of the autotiler, but the models and the basic kernel, they are open source, so you can actually go in there and add support or change if something is not suiting you. So this is then, I mean, I can send you a complete list of all what we support. I think I don't have it in my backup slides, but I can provide it.
Can I find it on your site? Yep. Or on the GitHub? Yep.
Okay.
The list of the supported operations. Yep. Am I right?
Sorry, I didn't get you.
Can I find this list of supported operations on
I-
your website or not?
I don't know. I have to check. I don't know if it's on the website. I'm sure that I have it, but I can provide it.
Okay, thank you.
Hi, Francesco. So the
Hi.
question is that it's not related to your device, but do you have problems with production of your devices? With all the problems with chips that are
Yeah, the shortage you're talking
Yep.
about. Yes, I mean, in a sense that from one side we think we are quite lucky because from one side all the we forecasted for next year is something that we checked with our chip provider, and it looks like it's we're gonna have the furniture of the chip. In the meantime, we are also looking forward to have GAP9 in production next year. And for GAP9, which is something which we didn't forecast it at all in terms of sales because it's not yet a product. This is produced in global foundries and with a technology which is called FDSOI and which is quite a new technology. So there is not a lot of, for example, of chips in automotive or in big market that uses the technology. So we think that for that, we don't gonna have shortage. While for GAP8, if we have to provide the new chips, which we don't have forecasted next year, yes, we probably gonna be in kind of trouble. So we see it also for us, yeah, in a sense. But yeah.
okay. So, and do you have any plans about GAP9? So,
yeah, we have plans. I think that we're gonna have it in I mean as a product, and that can be an EVK, so development kit available on our website by the end of the second quarter next year. So this is a little bit the when we plan to release it publicly.
okay, great, thanks.
I have a question regarding quantization. By your experience, how often it's enough just to use the floating point model, then pass through your toolkit and receive good accuracy quantized model? Or what range of tasks it's really working, or how often it's needed to provide quantized model by yourself before the toolkit?
So with the we moved to this new SQ8 schema. So this is related to asymmetric quantization. You still in big network have a little bit of drop in accuracy, maybe 1-2 percent. And I'm talking about CNN. So in CNN, it's a lot of stuff is going. I think we have also been working quite some years on this point. While if we move to LSTM, so to RNN, this is quite a lot more tricky. So even, I mean, there's not a lot of support for quantization. And also, since you are looping a lot on data, this is actually causing the fact that probably you need bigger activations. And so we are actually actively working on it. So I would say that for CNN, I think that quantization could impact, but not that much. So if you can make a product out of it, and then you can always improve to have quite the same accuracy. While for RNN, this is more tricky. So we are also working to understand if there are, I mean, there is a lot of work related to having temporal convolutional networks, but so that have a CNN structure, but that can replicate an RNN, let's say, way of functioning. The thing is that you still don't have this status. So these are points we are working on.
Thank you.
Okay, if there are no more questions, we can finish. So exactly 17:30. So perfect timing. Thank you, Francesco.
Okay,
for this
thank you.
talk.
Thank you very much. And have a good afternoon.
You too.